Hi, Jeff Disher here again. Because of all the popularity for the CPU architecture talk, I wanted to do one on a very related issue, which is the modern CPU performance concerns. So what I'm going to talk about in this is a bunch of things which are either of interest now or very recently were, and you still hear them talked about from time to time. So first of all, we're going to talk about 64-bit processors and what that means, what the performance benefit or drawbacks are of that decision. Memory density and cache utilization, because that's an increasing area of interest and performance concern as time goes forward. Also multi-core, because that's something that is very common in mainstream processors today. And simultaneous multi-threading, which if you're familiar with terms like Intel's hyper-threading, this is the generic term for all those kinds of technologies. And that's used fairly commonly today as well, especially in some of the higher end processors like i7s and stuff like that, and some of the new Spark processors. So first of all, 64-bit. Right, well, why is this needed? We've been using 32-bit processors in mainstream computing since the 90s, and the problem that we were running into was twofold. Basically, it comes down to 32-bit numbers can only store, or 32-bit registers, the component on the CPU that stores data and that operates on data, can only store numbers between 0 and 4 billion. So this was starting to become an issue because of primarily memory. 4 billion means you can talk about memory addresses up to 4 gigabytes, and that's it. Then after that, things get a little complicated and might not even be possible. So it depends on the architecture and the kind of environment where you're operating. So also, the math with very large numbers is very slow in 32-bit because you have to do it in pieces and then put those pieces together. If you have 64-bit registers on the chip, what's called a general purpose register, because we use for just general purpose things like talking to memory and doing simple math, then that can become an issue. So this helps in that situation as well. However, in the general case, it's not really, those issues aren't very meaningful. Most programs don't need more than 4 gigabytes of memory. That's pretty unusual. And also, usually large numbers aren't being used, or if they are, they're a completely different kind of number that doesn't operate this way and does not use general purpose registers. So, but at the same time, we're talking about pushing around twice as much data. The numbers are now physically larger. So they use twice as much data, which means they use twice as much cache space and twice as much time on the memory bus. So doesn't that make everything slower? And the answer is, well, yeah, in general it does. On the x86, however, they also, when they switched to 64-bit implementation, they added more actual registers to the chip. They really didn't have enough, and it was starting to become a big performance penalty for them, what is referred to a lot in the literature as register starvation. So they added more registers when they changed to 64-bit, and the performance benefit they got out of that was much greater than the performance loss from going to larger numbers. There's various attempts to maximize these two competing problems by saying, well, what if we could just use the extra registers but not use the bigger memory? Wouldn't it just be a lot faster in that case? And yes, it is in most cases. There's something that the kind of most ambitious version of this I've seen is what's called the X32 ABI, which is something on Linux that they're playing with, where you actually can do that. There's some stability concerns with some programs, but it is supported by the kernel. And it is a compelling idea. I think it's kind of neat. If it had come out a few years ago, it would have been more beneficial, but it still helps. So this all really comes down to memory and cache, because that's where we're getting the loss in 64-bit. If we're just moving around more memory, that's what's hurting us. So what can we do about that? Well, one of the things to remember that's been true pretty much forever, at least for a few decades, is memory is slower than CPU. And relative to CPU, memory is always getting slower, realistically. It has some of the same fundamental limitations that CPU speed does, except that it doesn't have a lot of the advantages that CPUs do either, in terms of tricks you can play to make them faster. So memory is slower. It's what we refer to as memory getting further away. So what we try and do is put some memory close. We use a cache, which is just a small piece of really fast memory, and these days that's usually located directly on the processor. In some cases, and historically it not necessarily was, but one way or another it was basically a small amount of fast memory. But the problem is cache is a finite size, you end up doing what's called an eviction of old data. Every time you need new memory that isn't in the cache, you evict something old that you haven't used in a while, or that the CPU determined you're probably not going to need for some reason, and you load the new data in there in the operating cache. So the more data or the more code you have on the CPU causes cache pressure. This more data is where the 64-bit problem starts to bite you for memory bandwidth concerns here. And in terms of further terminology, too much cache pressure causes what we usually just refer to as cache thrashing. It's not really a technical term, it's just what I tend to use when describing it because that's commonly what people talk about when they're working in this area. So now we understand that problem. What are multiple cores and why is that big and why are we using that? Well, first of all, you have to understand each program consists of at least one of what's called a thread. This contains its state, what it's doing, what it's currently operating on, and things like that. Now, because of the nature of this, one thread can only be operated on or executed by one core at a time. This means that if you have one thread that's doing a lot of work and you add an extra core, it still takes just as long as it did before because that other core can't do anything, it just sits idle. So this is kind of one of the fundamental problems in sequential programs is that the more CPUs you add, one heavy thread doesn't get any better. Further, as you add more cores, this does also increase the cache pressure because in a lot of situations, the cores actually share some or all of their caches. There's reasons why this is a good thing, but there's also reasons why it's a bad thing. So this causes increased cache pressure, so you're more likely now to fight over the cache resources between different cores. Also, you have more cores to access memory. So even if they're not sharing the same cache, what happens when you have 4 cores and they all need to access memory at the same time? Well, in most systems, the way most systems are designed, only one CPU can access memory at a time anyway. So now they all have to line up and they get it one at a time. So this causes a serialization which is very, very slow. It really punishes you in performance. So symmetric multi-threading, or just as it's called often SMT, it's sort of another way of how do we maximize what we can do with the CPU resources. And this also keeps coming back to the issue of, well, what do we do with memory? How does memory work? But basically what this comes down to is you allow one CPU core to show up as though it were more than one when talking to the OS. So the operating system will see one core, but the core will tell the OS that it should actually treat it like it's 2 or 3 or 4. Actually, in some cases, I think go up to 8 these days. But and then it can run more things there. So how's this beneficial? Well, because it seems like if you're just running more threads on the same core, you should just run out of computational resources, right? There was a reason why there's only one core in the first place. And one of the main benefits here is what's called an unused superscalar resource. If you remember before, I had a quick allusion to the notion of superscalar, which is in a CPU where you actually run multiple instructions at a time. Well, we've been doing that for a long time in CPUs, and it got to the point where you'd have so many different superscalar, what's called pipelines, that could execute individual instructions that you often couldn't use all of them at once anyway. There was just a reason, like, okay, you didn't have those kinds of instructions to run right now, so some of the superscalar resources would just be idle. So in SMT, part of what they say is, well, if we had another thread that's doing something totally unrelated, maybe it can use some of these resources. So you actually get what's essentially called free computation, because you're now getting more done, but you didn't do anything. Nobody got hurt. You didn't take anything from anyone else. It was non-zero sum. You just got something for free. So it's kind of it was a clever idea. And there's other things too that can improve it, just because of things like the order in which the different threads are trying to access memory. One might get stuck waiting for the cache to refill, but the other one isn't, so it can run freely. The OS not having to know about these details of how you're implementing it gives the CPU a lot of freedom to run really fast and be able to switch between these threads, sometimes within a few instructions, sometimes running multiple at once within different threads. But the downside is, of course, like everything else, it increases cache pressure. Because now you're doing more things with the CPU, more independent operations on top of that, each of those things is going to be wanting to bring in its own memory, bring in its own code, and do things that way. So it does increase cache pressure, which can mean that you end up punishing the other threads that are running there. This is why you often end up with a situation where SMT yields performance which is worse at one task than not doing it at all, but better at doing multiple. Substantially better, in fact. In modern implementations, the worse at one task is not a big deal, but better at multiple is definitely something you see. So it's beneficial trade-off, and yeah, you see it a lot in high-range workstations and even some mid-range computers. You end up seeing this, like like I said, anything with Intel hyperthreading, that's using this. So it's a clever idea, and it gives you a real benefit in a lot of cases. So that's just sort of a discussion of a few of the issues which have been sort of, they're interesting CPU architecture and CPU performance concern ideas which have been in kind of the mainstream consciousness for a few years now. And there's lots to talk about with them, and people are doing a lot with them still. So anyway, contact me or leave a comment if there's something else you want me to talk about, or if there's further questions on these topics that need to be dealt with. Anyway, thanks for watching. Hope you enjoyed.